Hello there. In this lesson, we're going to look at the quantum numbers that go with the electrons in an orbital box diagram or energy level diagram. And then we're going to relate that to some properties of elements like magnetism. So if you recall, there's four quantum numbers that you've learned about. The first one is the shell, right? The second one is the subshell. The third one was the orbital. And the fourth one was the spin, m sub s, right? And so being able to assign all those and then look at how the electrons are all oriented will help us to explain some properties like magnetism. So one analogy that I kind of like for quantum numbers is thinking of them as an address, like an identifying set of values that will help you to place a certain electron in a certain place around a nucleus. And so we've got our shell numbers, right? And so those are all the layers, 1, 2, 3, 4, 5, 6, 7. And those sort of correspond to the levels on your periodic table if you count down the side. And then we got our subshells, and those also correspond to sections of the periodic table, as you've come to learn. Finally, we got our orbitals, and so that returns to the idea that electrons will end up in pairs. And then in order to have them in pairs, they have to have opposite magnetic properties. And so you can kind of think of this as being like a neighborhood of electrons, and the lowest energy electrons would be at the bottom here, shell number 1, subshell number 0, and so that'd be like this location. And you can put up to 2 electrons into that orbital. Or you can move up a little higher. This is like shell number 3 and subshell number 2, and maybe it's in this orbital, in which case you would go to shell number 3, dorm number 2, and you're in the second orbital over here, and that'd be an electron there. So they're all like different locations representing electrons with different properties around the nucleus. So let's assign a few quantum numbers here. Just a reminder, the electrons within the same orbital can't have the same spin. And so that means that no two electrons in the same atom can have all four quantum numbers being the same. So let's pick a few, which I have here already, A, B, C, and D. Electron, the first here, electron A, is in the first shell, so n equals 1. First subshell, so L equals 0. I like to label them right on the orbital box if that helps. You can do that too. So orbital number 0 as well. And we will, by convention, just say that the downward spin is a -0.5 for this electron. Alrighty, so the second one here is also in an s orbital. So this is just 2, 0, 0. This time it's +0.5 because the arrow is pointing upwards. Here we're still in shell number 2. We're in the P subshell, so that's subshell number 1. And then I like to label them. Sorry, this would be -1, 0, and +1. So this is orbital number 0, and then it's a spin down for the downward facing arrow. And the last one here we have is in the third shell. It's P again, so that's L equals 1. If we label these orbitals, this is the -1 orbital, and then it's spin up to finish things off. There you go, hope that helps. So the periodic table, of course, is also arranged by shells and subshells, and so you can use the periodic table to assign quantum numbers, especially for the last element in, last electron in a given element. So we're going to start with sodium here, and you can see sodium is over in this section. And so this is 1, 2, 3, S, because that's the block that it's in, right? So shell number 3, S is 0. The subshell and the orbital are both going to be 0 for S. And then the spin is, if you just look at the order in which they go in here, this is going to be the up arrow first and then the down arrow second. So we'll call this +1/2 for that last electron to go into sodium. Let's try another one. Iron is over here. This is the 3D subshell. And so that's n equals 3, L equals 2. and then you can assign orbitals starting at the beginning of the subshell. So this would be -2, -1, 0, 1, 2, and then back to -2 to do the second set of electrons, -1, 0, 1, 2, and so forth, right? So it's an orbital number -2, and then because it's the second electron to go in there, it's going to be the -1/2 for the spin. Sulfur over here, this is 2p, 3p, so we're in 3p. And then again, you can assign the orbitals, so it'd be -1, 0, +1, then back to -1, 0, and +1. So that means that sulfur is in the -1 orbital, and it's the second electron, so also -1/2. Finally, let's look at arsenic, right below sulfur there and to the left. So this is 2, 3, 4p, and so that's shell number 4, p is L number 1. And then if we look at the orbitals, it's going to be -1, 0, and +1. So that means we're at +1 here. And it's the first electron to go in there, so it's +1/2. So give that a try, and you might find it helpful rather than drawing out the entire orbital box diagram for the whole thing. You can do a shortcut with your periodic table. So it turns out there are a few places on the periodic table where the Aufbau principle is not followed, where sometimes electrons will be placed in higher subshells than they would according to the patterns that we've been following. And so a couple examples are chromium and copper. So chromium and other elements in that same column can have a slightly unexpected orientation of their electrons. So you might expect, if you're just following the Aufbau principle, that by looking at chromium there, that there should be, 1, 2, 3, 4 electrons in that D subshell. But what they find is, rather than having a full S shell and almost full or almost half full D shell, is that one of those electrons is actually placed in the D subshell so that it is half filled. And so this must be because it's of lower energy overall for the whole group of the electrons together, and having this completely half-filled d orbital makes the atom more stable, and so that's the way you find it. Same thing happens with copper. You would expect 9 electrons in D, something like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. But what you actually find is that a half-filled orbital before the half-filled S and a completely filled D must be more stable, because that is the actual way in which it is found. So there are a few places on the periodic table like that where it deviates a little bit from the pattern that we've been following to this point. I found this little periodic table to be kind of useful to highlight the places where the Aufbau principle is kind of not followed. So you can see there's the chromium column there, and instead of it being 3d4, there's actually 5, and you see the element underneath is the same. And then over here in the copper column, and there's silver and there's gold, they all follow that same pattern of pulling an electron up from the s orbital and having a full d. And then there's a bunch of places where you see that it doesn't follow the pattern down here, lower down. So I'm not going to ask you to memorize them, but just understand that there are a bunch of places where the pattern doesn't seem to follow the usual, right? There's some 14s where it should be 13s, and there's some 7s where they should be 6s, etc. And so just understand there are a few places that don't quite follow that pattern that you might expect. Okay. So magnetism is a property of matter that is easy to observe and has lots of uses, from like fridge magnets to electric motors to a compass, if you've ever used that. And so I think a compass is a good example of how smaller magnetic components can be related to others that are much larger. So what happens is, at the atomic level, different configurations of electrons will make each atom have a small magnetic field, and you'll get like a north and a south for each atom, right? But the atoms aren't all necessarily oriented the same as each other until you put them into a magnetic field that gets them all to align. And so what happens is, just like if you have like a small compass in your hand, the needle on the compass will align with a much larger magnetic field that exists around our whole planet. And we know there's a north and south pole to our planet due to the orientation of all the little magnetic components, mostly in the core of the Earth near the center. So it's all those little small atomic little magnetic dipoles that end up getting aligned to form a much larger magnetic field that can be measured externally. And so it's those big magnetic fields of like kajillions of atoms, all with their little magnetic fields aligned, that produces the magnetism that we see and that we use for all sorts of neat applications. So our first type of magnetism we're going to look at is called diamagnetism, and this is very weak, and it is the result of having no unpaired electrons. So if you look at calcium or zinc, all of the electrons, even in the valence shell of calcium and zinc, are all paired. There are no magnetic fields that aren't sort of canceled out by having the spins of both electrons opposing each other. And so this results in producing a magnetic field only when other stronger magnetic fields are close by that oppose an external field. And so there's always going to be this repulsion that happens. Bonded molecules will also have this. So, of course, all organic matter, water, anything that's bonded generally has all the electrons being paired, and you'll get a very weak repulsion if you have a strong enough magnet to measure that. Paramagnetism is a little closer to the ones you're used to that you stick on your fridge. These are kind of like temporary magnets. They have very few unpaired electrons, and so they have a weak attraction to magnetic fields. And as soon as that magnetic field is removed, well, then the magnetic property of the paramagnetic substance is lost. So if you look at sodium, it's got a single unpaired electron. If you look at aluminum, it also has one unpaired electron. And so if you have like a single unpaired electron, it means that you're going to have a little bit of magnetism for each individual atom. And then if you put a bigger magnetic field around it, just like the compass in the field around the Earth, they'll line up somewhat and you'll get a little bit of attraction. As soon as you remove the magnetic field, well, they all start to go random apart from each other, and the magnetic field is lost. So the last type of magnetism is called ferromagnetism. That's the one everybody's familiar with. Iron and steel and all those neat things that have iron as part of them all have the potential to be magnetic substances, and that is because iron has lots of unpaired electrons, 4 to be exact, that produce this strong magnetic field around each of their atoms. And then if you get each of the little magnetic fields in those atoms aligned with each other, then you can end up with a whole substance that is magnetic. Neodymium is those new strong magnets that you can get, and it too also has 4 unpaired electrons in the F subshell that allow it to do the same thing. So what happens is you'll have groups of these atoms, or domains, that'll have the atoms' fields are all aligned within them. And then if you heat it up and put it into a strong magnetic field, you can get all of them to align, and you'll end up with a substance that will keep its magnetic field permanently. And so those are the substances that you might use to stick notes to your fridge. So the result is a stronger magnetic field that can be used to magnetize other things. A neat experiment you might want to try is making a compass out of a magnet and a needle. You can check that out on YouTube. Good fun using ferromagnetic substances.